Oh, welcome everybody. Sorry about the delay. We seem to have lost my slides, which will make this even harder without, so we found them. I'm going to be talking today as a brief little security update on the Zephyr project. My name is David Brown. I have a lot of hats. I work for the security working group at Linaro. I'm also kind of on loan to the Linaro IoT group, Light. I am the Zephyr Security architect for the Zephyr project, and probably other things that aren't relevant to the talk as well. To begin with, what's Zephyr? Who knows what Zephyr is? Just get an idea of, I think everybody probably does. Zephyr's this is copied right off of the webpage at the Zephyr project. But important thing to remember, Zephyr's not Linux. Zephyr is an open source real-time embedded operating system. And there's a bunch of links here for when these slides come out for more information. So what are we doing about security on Zephyr? Part of the charter for the Zephyr project is the creation of this Zephyr Security subcommittee, which usually gets called the Security Working Group, which makes it confusing because everybody else calls theirs that too. So the different levels of engagement in Zephyr, the Platinum members each get a seat on this security subcommittee, and then Silver members get a seat by invitation to the committee. And then there's two elected positions. There's a chair who runs the meetings, takes notes, that kind of thing. And then there's the security architect, that's me, and who's responsible for overall project security. The idea is, theoretically at least, when people have a question of, well, how do we do this securely? I'm supposed to be able to answer that. So this can be really basic. What have we done? Where are we at now? And what do we expect to do? Real summary of the whole talk. We have a security subcommittee that meets bi-weekly. We have a call, a bunch of people dial in. We cover a lot of different topics. We've created a secure coding practices document that describes, it's mostly copied from other projects, which is a really good way to say things coherently instead of your own new thing. And it's a bunch of documentation on how to write secure code, which is actually really hard to write down. A lot of it is very subjective and based on experience, and some of the projects that we took that from encode that pretty well. We just recently got a registration with MITRE as a CVE numbering authority. It's a lot of letters and a recursive acronym that basically means that we can allocate our own integers. So when you see CVE 2019-116 or some particular number, we allocate that ourselves we ask for a block and then we allocate those and update the data. With that, we have a publicly documented process. If someone reports a vulnerability, this is the steps that it goes through. There is a JIRA instance that allows these issues to be marked private during an embargo period, because often security issues are sensitive, and you want to be able to roll out a fix to certain customers, to people, without broadcasting to the world for some limited period of time, usually 90 days, that, oh, there's this vulnerability, but oh, now it's fixed. So there was a vulnerability that we don't have anymore. A couple other things that we've done. The CII, the Common Infrastructure Initiative project, is a series of best practices. It goes over multiple levels from, I forget what they are. The laptop one is gold. There's silver. I forget what the first one is. And there are different criteria for things from, is your project website secure, to do you have these kind of things in your process documented. It's pretty basic stuff. Do you have a public repo? And we have managed to get the gold for that. This is also a link to that. And there's a good number of projects that are now following this, not that many that are gold yet, but it's a good goal for kind of an overall project-wide, not as much the code specifically, but to make sure that you have a process so that contributions making it into the code have known authorship, that kind of thing. And we also have automation set up to prevent regressions. Basically, you compile and test the code, or automatically compile and test the code to make sure things don't break. So we use Git. Code is on GitHub. And the main branch where development happens works like a lot of GitHub projects. There's pull requests, code reviews, the CI process runs, and this goes into this development repo, and there are releases from it. We now have a long-term release, which I'll get to the details of that in a second. But the idea is this is a stable version, and if you're building a product, it's good to start from this because there will be less change in patches. Then the other one here is this completely mislabeled one that's supposed to be auditable. I don't know, my diagram is wrong. The third one is supposed to be the auditable branch, and the idea is this is a subset of the repo that can pass additional scrutiny to make it easier for those customers that wish to build something that can be certified. I'll get to that in the details of that in a minute. So this long-term stable one, the one in the middle, the idea here is it's product focused. We do keep up with security updates, so there's arrows coming, feeding into that whenever there's a security fix, those will be backported to this. Interestingly about this, that I think is kind of unusual, is we also add new hardware support to the long-term stable tree. The idea that these are lower risk things, I guess would be the way to describe it, that new support for new hardware can be backported to the long-term stable tree. The idea this is more tested than the regular release branches. It goes through a longer beta cycle. Importantly, this is not a feature-based thing. It's not about introducing new features, and it's not cutting edge. This is kind of what you would normally build a product around. Then in addition, we have this auditable repo, and so these are branches off of the long-term stable, and it significantly is a subset of the code, frozen in time, and it's intended to be certifiable. So if you need FIPS 140-2, FIPS 140-3, the idea is you can start with this, and it should be easier to get to that point. Yeah?
So frozen in time, you need no security updates?
What kind of updates? Okay, yes. So the question is, will this auditable branch get updates? Yes, security fixes will go into that. Not much else. It's kind of frozen. There's an example of this was done with OpenSSL. There's a FIPS 140-2 subset of that was certified. It's fairly old now, but that still exists and is maintained. Any other questions? So that kind of covers where we're at now with the project. As far as ongoing work, what are we doing right now? So there's project documentation that describes security. And so all of this stuff I'm talking about here should be visible there. So just a couple of things from here. We have these coding guidelines, which I'll get to a little bit more on subsequent slides. We've documented things like how do you report vulnerabilities, the process for a secure bug, and the Jira instance I mentioned for bugs that go through an embargo. So the idea is you can go to this document. A lot of this is required by that MITRE process for the CVEs. So someone can go read our documentation, and they send a vulnerability to us. They have some idea of what to expect. The person who reports the vulnerability will have visibility to the Jira instance as it goes through the different stages and ultimately ends up as either rejected, typically because it doesn't even apply. We get a lot of those because we have, say, a Bluetooth stack. So a ticket will get created for each time there's a Bluetooth vulnerability, and then a lot of those don't apply because that code is not relevant, or we wrote it after the vulnerability was discovered. That was a recent one that we rejected. Ultimately, this ends up either in that rejected state or we're done, it's public. The CVE will be updated, and then that Jira page is then publicly visible and can be linked to from external resources. So we've done this. We've had our last release, 1.14. There was a handful of CVEs that were completed. I've gone through the process of learning how to update those. So if you type those CVEs into well, just type them into Google and it takes you to different search engine pages on that with all the links back to the release notes, to the patch. So it's kind of a nice interconnected. The idea is that if you have an old version and you want to fix it, you have enough information to figure out how to backport that yourself. So, trying to keep an eye on the time here because I wasted a few minutes at the beginning. As far as coding guidelines, I have strong opinions about coding guidelines, and it turns out everyone else has strong opinions, and they all conflict, and they don't get along with each other. So we want to not invent them, I think would be the idea there. This is not like how do you indent the code. That's covered as part of there are coding guidelines in the code for that. But from a security point of view, kind of the big document is this MISRA-C 2012. It's a standard of things you shouldn't do in code, formalized a little bit more to where you can check, does the code do those things? And there's an amendment to that. And then a couple other documents, this SEI Cert-C and JPL wrote some docs on code. The idea of these is by following these, it gets rid of a lot of easy security fixes. They don't make your code automatically secure when you have them, but it makes the code easier to review, especially if there's something that is easily violated by that, you can just point to this coding guideline. But the important thing is we need to be able to enforce these. When you submit a pull request, a tool can come back and tell you, well, you violated such and such in the code. Go fix that before we have to look at it. So we're kind of gradually imposing these. They're not, here's 100 things we're doing to the code, because as soon as you start running these tools, you find, oh, look, we have 1,053 violations of this particular requirement. Well, we have to fix those before it even makes sense to start enforcing them. So this is kind of an ongoing, gradual process. I wanted to give an example of this whole, how does this security process work? There's a PR that's linked in the documents, and it updates the entropy and the random framework. So there's actually a couple of security issues that were discovered that get CVEs assigned to them. There's JIRA tickets about these. They're not published yet because this is still in the process of being fixed. And this has become this was a topic of discussion during our security subcommittee. In this particular case, it was a little easier because the code was worked on then by somebody who's on the security subcommittee. The goal of all this, in addition to fixing these particular issues, is to clean up the API and the documentation so that it's easier to do the right thing. Because it turns out we had these kind of misleadingly named functions for entropy, and it wasn't always clear which one you should use, and several places the code made calls to essentially a non-cryptographic random number source when they needed cryptographic random numbers, which I guess is sort of revealing a embargoed vulnerability. Oh well, you don't know the number. So what are some of our upcoming goals? There's just a couple I'll go through. One of them is variously gets called crypto drivers, crypto API, this kind of thing. We have right now 2 crypto libraries. They're available inside of Zephyr. There's TinyCrypt and Embed TLS. There's a little bit of work in there with a driver to do hardware accelerated support, and nobody actually calls it. So that's kind of a not success story of an API. This is a very active, ongoing discussion. The Embed TLS project and other efforts from ARM with PSA are kind of developing a crypto API, and we're evaluating, is it just appropriate for us to just use that? There's some kind of push as far as making an API that's specific to Zephyr so that we can easily switch between these different implementations. And at this point, where we're at is we're documenting what all these requirements are, what are the current statuses of all these, and then from that we'll have kind of a recommendation that we'll then present to the steering committee. This is what we think we should do. An additional aim is in regards to FIPS 140-2/3. FIPS 140-3 is effective September 22nd, which, if you look at the date, you'll notice is yesterday. I haven't looked at it yet. The documents were actually, the main document has been available for a couple of months, but it's basically references to about 12 other documents that have not been available, and they're all supposed to be available now. So I definitely didn't make it into the slides. I guess I was supposed to have something to say, but I don't. But the idea behind this is it's a standard used to certify cryptographic modules. These are traditionally isolated devices. Think of the card that sits inside of an ATM machine to provide the cryptographic primitives for that. It is a lot more general than that in application now, and the standard is also used because it's a good way to specify a certain base level of security out of some other projects. So a lot of other things, the Bluetooth spec says, oh, the random numbers must be compliant with FIPS 140-2, the various standards associated with that. So the FIPS process is about a product. You make this product and then you certify it, and then you can't change it. That's a little weird with an open source operating system. So the idea was to have this auditable code base that can then, the way we describe it is certifiable. It's not that we have certification on that, but that it's a really good starting point. If you want certification, hopefully the certification labs will become familiar with this code base, and they won't have to check the same things again and again because it will be used multiple times. The focus of this is on cryptographic operations. There's other topics on safety that cover a lot of other aspects of the code too. So an additional aim, I'm sure I'm doing okay, I have a couple minutes. For secure boot, I've given a couple talks on MCU boot, so I'm not going to review all of that today. But what we have now is the MCU boot bootloader is supported by Zephyr, boot revertible upgrades, signed images against a public key in ROM, and it's now being used by Trusted Firmware M as part of their secure boot update process story. So that's good, it's all in place, but there's a lot we need to do. We need a full story. So instead of, right now I test the bootloader by using a JTAG debugger to load an image into the second slot, and it updates that. But it's not particularly secure because there's nothing to stop me from replacing the first image with the JTAG debugger. So there's some pending patches in the tree and some ongoing work of standards for how do you download images from the net, how do you know what's available. There's an IETF working group for SUIT called the Software Update for IoT that's defining some of those, and a lot of that needs to be implemented. It's not finalized yet, so it will probably change. Just learned of an additional requirement for a much richer key infrastructure. Instead of one key that's stored in ROM and everything signs against that, people need hierarchies with a kind of an infrastructure of keys. I think there's just a couple more left, so I'll go quickly here. There's some work coming in on the topic of fuzzing. If you're not familiar with fuzzing, the idea is you generate garbage, random inputs to a module of code, and you make sure it doesn't break, you don't damage it, that it doesn't introduce security vulnerabilities. Turns out this is really hard to do on these little microcontrollers. Most of the work is done on great big systems where having a chunk of LLVM linked in with your application is not a big deal. That doesn't work really well when you have a megabyte of code space and 16K of RAM. So there is a research project from, forget what university, that had been putting a fuzzer kind of molded in with QEMU to do the fuzzing on a bigger machine. some other possibilities of using the POSIX native port for some aspects of fuzzing. And really what it is, this is a big area for research, but it's something that we're talking about in our security meetings because it is a great way to find vulnerabilities. Lastly is documentation. What do we want to do with it? We wrote up some threat models, or should I say I wrote some threat models a year and a half ago, 2 years ago. Since then, I've actually learned what a threat model is. And part of the effort is to go through the threat models that we have and kind of rewrite them so that they read like threat models. Additional things are to define some threat models for other kinds of contexts. It's hard when you have a generic operating system. What is the threat? Well, depends on what they're using it for. So kind of need to pick specific applications and create some more of those. So that's where we're going. I think I have 0 minutes for questions if you have any. Very fast questions. Otherwise, I think that's probably about it. You can ask me questions afterwards too. Thank you.